So the next topic we are going to see is that of losses in pipe flow. So if you think of a piping system, you have a pipe and then you have, let's say, an elbow that turns the pipe by 90 degrees, and then you have further piping section, another elbow, or a valve or a split or a Y section, and so on. So we classify losses into two types. One is called major losses, that is due to friction between the fluid and the walls of the pipe and the walls of the pipe. Sorry about that. And then we also call one type of losses as minor losses, that are related to mixing, sudden expansion or contraction, sudden movements, and inertial losses, or losses due to shape of the structure. So we are going to look at both these type of losses. We'll say there is a head loss of HL, which is equal to the H major plus H minor. Now what is this head loss? We need to think about what is head loss. So if you recall your Bernoulli equation, you do know that it's applicable only for the inviscid situation. If you have a streamline, you have point 1 and point 2 along the streamline. Your presumption is P1 plus half rho V1 squared plus GZ1 plus rho GZ1 Z1 equals P2 plus half rho V2 squared plus rho G Z2. This is the Bernoulli equation in which there is no viscous effects or no friction. Now you can extend this equation to a practical flow which has viscous effects. If viscous effects are present, if you have a station 1, let's say you have station 1 and then you have station 2, you can write this as P1 plus half rho V1 squared plus rho GZ1 equals P2 plus half rho V2 squared plus rho GZ2 plus a head loss between 1 and 2. HL is the total head loss between 1 and 2. So we are going to write it in a slightly different form. We'll write HL multiplied by rho G, okay, so that dimensionally both the sides are consistent. If I write this equation differently, if I write this P1 minus P2 divided by rho plus G times Z1 minus Z2 plus half V1 squared minus V2 squared, I can equate this to HL, or the total head loss. Okay. Now most of the time if HL is estimated, if HL, the head loss, is estimated, one may compute either the change in pressure or the change in potential energy or change in elevation, or the change in kinetic energy or change in velocity. Okay, so how to calculate the total head loss, which has units of meter, is our task here. We are going to split this task into two parts. HL, I told you, consists of a major loss coefficient and a minor loss coefficient. And major loss coefficient consists of skin friction or viscous losses. Okay. For pipe flow, if you have, let's say, a pipe flow over a certain length L, and the pressure drop driving this flow is delta P, okay, is delta P. Delta P is P1 minus P2, and the fluid flow velocity is on an average, that is, the average flow velocity is V. So in this case, the pressure loss, or delta P divided by rho, may be written as a friction factor F times L by D times V squared over 2G. Now what are these terms? Delta P is the loss of pressure head due to friction. L is the length, D is the diameter of the pipe, V is the average flow velocity, and F is the friction factor that is introduced here. F is to be calculated either from theory or computations, or somebody has to do experiments and needs to be tabulated data. By some means, F needs to be estimated, and F is the pressure head loss delta P by rho, which is the head loss or the major head loss, is given by F times L over D V squared over 2. That is, focus on your task. Your task is to get this. This, I'm going to show you a lookup table on how to get this. These are all parameters that are known. Okay, so this friction factor is our big unknown here that we need to estimate.